Welcome to our class notes 4-5. These class notes are really important, as this particular set of notes is the launching point for everything that we're going to do in the remaining part of Unit 4 and for all of Unit 5, and really for a lot of units that will follow even after 5. So it is important that you have an understanding of the things that we're going to be discussing today. As we go through these notes, I encourage you to print out a packet of notes, or be sure that you mark in your notes anything that you might be confused on so that you can ask about it later. Don't hesitate to ask questions on any of this that is confusing to you. It is very important that you watch this. There are a lot of notes, or there will be a lot of videos associated with this material. I encourage you to watch a video and to be sure that you're focused when you're watching the videos, to take breaks as you need, to replay the videos as you need. Don't try to sit down and watch all the videos in one session. You can watch a video and come back later and watch the next video. You can even take breaks mid-video if you know that you're having trouble staying focused. But hopefully you won't, because the questions we're going to be answering in today's notes are great questions. We're going to start getting into why is it that the first level holds 2 and the second level holds 8? Where are these numbers coming from? We're going to get into why atoms are stable with 8. We're going to get into why the third level can hold 18 and the fourth level can hold 32 electrons, yet they're stable with 8. We're going to begin to see where these numbers are coming from that we introduced earlier this year. And this was all answered when we get to the fifth model, the final model of the atom, Schrodinger's model. Heisenberg's given credit for this model as well. This is the quantum mechanical model of the atom, also called the electron cloud model. But before we get to the fifth model, it's important to see where this fifth model came from. And maybe one of the best ways of doing that is taking a quick look at the models of the atom throughout time. The original idea of the atom came from Democritus and Leucippus, ancient Greece, somewhere around 442 BC. That is going back 2,000, well over 2,500 years. And this model, the idea that there is an atom, was just really a notion that came out of discussions about what makes up things. And Democritus held the idea that if you took matter and continued to cut it up into tinier and tinier pieces, eventually you would get a piece so small that you could no longer cut it up and still have matter, still have that substance. And that's where the word atomos came from. Atomos means indivisible, not invisible, indivisible, meaning that it can't be divided, or uncuttable, meaning that you can't cut it up into smaller pieces. So Democritus had this idea a long ago. Leucippus was like his mentor that he talked about these things with. And this idea came out long ago, but the idea never took hold. And that's because some incredibly famous Greek philosophers, Aristotle and Plato, argued against the idea of the atom. Because they said if you could cut up matter into smaller and smaller pieces, what was it then that would be holding all those atoms together? Democritus's model was indestructible, it was invisible, as well as indivisible, and he did not even have a notion of subatomic particles such as protons, neutrons, and electrons. His model's kind of pictured as a ball. Well, why was the idea of the atom brought back? It was discarded for a long time. And the idea of the model of the atom, the idea of the atom was brought back in the early part of the 19th century in England by John Dalton. And Dalton's model is called the indivisible solid sphere, very much like Democritus's model. But Dalton realized that Democritus had to have been right, because there were some things being discovered in chemistry that would only make sense if all matter was made up of atoms. And those things that were being discovered right at this time, at the latter part of the 18th century and the beginning of the 19th century, in other words, the late 1700s and the early 1800s, some things were being discovered in chemistry. And they were very, very important. In fact, they became laws of chemistry. These are the fundamental laws which govern the subject of chemistry. Laws just means that it's something that happens every time. It happens always the same way. And it's usually something that, or it's something that happens in nature the same way. One of the first laws that led to the idea that matter must be made up of atoms was the law of conservation of matter or mass, discovered by the great Lavoisier in 1789. And what Lavoisier found out is that during a chemical reaction, mass and or matter, same idea, cannot be created or destroyed during the chemical reaction. In other words, whatever mass goes into the reaction must come out of the reaction. So for instance, Lavoisier would say that if we take 4.032 grams of hydrogen and burn it in the presence of 32 grams of oxygen, we would have 36 grams of water produced. So it went 4 grams, 32 grams, we would make 36 grams. Whatever mass went into the reaction came out. And by the way, this is the equation for the production of water through burning hydrogen. But whatever mass goes in must come out. Dalton said the only way that could be true is if hydrogen was made up of hydrogen atoms, oxygen was made up of oxygen atoms, and these atoms went into the reaction and they would have to come out of the reaction. So here's the actual equation for making water. This is the chemical equation. It's 2 molecules of H. Remember, hydrogen's diatomic, H2, for every 1 molecule of O2 to produce 2 molecules of H2O. That's the small scale. On a larger scale, we could say 2 moles of hydrogen would react with 1 mole of oxygen to make 2 moles of water. But since we're talking about things on the atomic level, because we're talking about models of the atom, we would see that 2 molecules of hydrogen gas, H2, would actually be 4 atoms of H. 2 molecules, each with 2 atoms in the molecule, would be a total of 4 atoms. 1 molecule of O2 has 2 atoms of oxygen joined. So we have 4 atoms of hydrogen going in and 2 atoms of oxygen coming in. And Dalton's like, well, that would explain it. We must have those same atoms coming out. H2O then is 2 H2O is what we made. 2 times 2 for hydrogen would be 4 atoms of hydrogen. The subscript for oxygen here is understood to be 1, and we have 2 molecules of water. Each molecule has 1 atom of oxygen. 2 times 1, 2 atoms of oxygen. Dalton would explain the law of conservation of matter by the fact that you can't destroy atoms in the chemical reaction. Whatever atoms go in must come out. This is how Dalton would explain it. He said it's the only way that this law would make sense. There was a couple other laws that were being discovered right around this time. A few years after Lavoisier's discovery of the law of conservation of matter or mass, in the 1790s, Proust discovered what's called the law of definite proportions, also called the law of constant composition, or sometimes just Proust's law. And what Proust said was that a given compound is always made up of the same elements joining in the same ratios by mass. What does that mean? Well, in this reaction up here, we talked about how to make water. What Proust would say is that to make water, you would always have to have the same ratios of hydrogen joining with the same mass ratio of oxygen. In other words, there's only one recipe for making water. Proust would say water is 8/9 oxygen by mass for every 1/9 hydrogen by mass. Where are we getting that? Well, you remember on the periodic table, hydrogen is about 1.008 grams if we round that up. If we round oxygen, we would get 16. Water, we know, is H2O. So there's two hydrogens at 1.008. That's 2.016. And there's an oxygen in there as well at 16. So 2.016 plus 16, water has a mass of 18.01 grams. But to make water, we would need 16 grams of oxygen right here. 16 divided by the total mass of 18. 16 divided by 18 reduces to 8/9 oxygen. What part of that is hydrogen? Well, we know that H2O has two H's in it. Each H is 1.007 or 1.008. We're just going to round that to 2. 1.008 times 2 is about 2. So it's 2/18 hydrogen. That's 1/9. Proust just says by mass, grams are mass. Water can only be made if we're putting 8/9 of oxygen for every 1/9 hydrogen. What does Dalton say? Dalton says that's because H2O always has the formula of H2O. The only formula you have for water is two H's for every one atom of O. It explains the law of definite proportions. Dalton himself kind of extended the law of definite proportions. The law of definite proportions is dealing with a given compound. A given compound always has the same mass ratios of the elements making it up. Why is that, Dalton says? Because the given compound always has the same formula. 2 hydrogens for 1 oxygen is water. But Dalton realized that if water is always H2O, a different compound containing H's and O's would have to have a different formula, or it would be water. And that became known as the law of multiple proportions. Proust actually had the data to prove the law of multiple proportions, but he never really turned his focus that way. Proust was always talking about a given compound, and Dalton realized then that a different compound made up of the same elements as another compound would have to have those elements joining in different ratios. And that's what he said here. The law of multiple proportions says two different compounds made up of the same elements must have those elements joining in different ratios by mass. So water, we already learned, was 16 grams of oxygen, 18 grams total. It's 8/9 oxygen. But what's the ratio of oxygen to hydrogen here? Well, it's 16 grams of oxygen per 2 grams of hydrogen. So it's 8 oxygen to 1 hydrogen. Here's another compound made up of hydrogen and oxygen. This is called hydrogen peroxide. Hydrogen peroxide has 2 oxygens in it at 16 each for a total of 32. It has 2 hydrogens at 1 gram each for a total of 2. 32 to 2 is 16 to 1. So what does that tell us? We have different ratios of the elements joining up because they're different compounds. It's 8 to 1 oxygen to hydrogen. It's 16 to 1 oxygen to hydrogen. And Dalton went on to say that the oxygen here is a whole number multiple. 8 to 16, that's a whole number multiple. Why? Because this has 1 oxygen, this has 2 oxygens. So the multiple, 8 to 16, is 2 to 1, the same way that this is 2 to 1. It works the same for carbon monoxide and carbon dioxide. Carbon monoxide has 1 oxygen in it at 16. It has 1 carbon in it at 12. 16 to 12 is a 4 to 3 ratio. If you reduce 16 and 12s, 4 goes into 16 4 times, 4 goes into 12 3 times. CO2 would be 32 grams. 2 times 16 is 32. Still 12 grams. So that is 32 to 12. That's 8 to 3. 8 grams of oxygen for every 3 grams of carbon. So if we look at these two ratios, this is 4 to 3, this is 8 to 3. This went up by a multiple of 2. The oxygen went up by a multiple of 2. Why? Dalton would say the formula went up by a multiple of 2. Because this formula has 2 atoms of oxygen, this has 1. That's the law of multiple proportions. We're going to continue with Dalton's model in the next video.